You know, the metal in our cars, our phones, pretty much everything we build, it all starts out as just plain-looking rock. So how in the world do we get the good stuff out and leave the worthless stone behind? Well, it all begins with a super important first step called ore concentration.
And that right there, that's the fundamental challenge, isn't it? We don't just stumble upon big, shiny nuggets of pure gold or iron. No way. They're locked away, mixed with tons and tons of useless rock. The real problem is just the sheer scale of it all. How do you sort through an entire mountain of rock just to find that tiny, valuable fraction? Okay, so first things first, let's get our terms straight. The ore, that's the good stuff. It's the part of the rock that has the valuable metal we're actually after. And then there's everything else, the dirt, the sand, all the other minerals we don't want. That's called the gangue. Our entire job here is to separate the ore from the gangue. So the whole point of concentration is to crank up the percentage of our valuable ore by basically just throwing out as much of that useless gangue as we possibly can. Think of it as the essential first cut before we get into any of the really complex chemistry later on.
To make this all super simple, let's use an analogy. Just imagine you've got a giant box filled with a random mix of heavy steel bolts and really light plastic nuts, but you only want the bolts. How would you separate them? Well, the methods we're about to look at are just really clever, industrial-sized solutions to that exact kind of sorting problem.
All right, let's open up our toolkit. Our first tool is the most intuitive one, the one that makes the most sense right off the bat. It leverages a property we all understand: weight.
This method, called gravity separation, works on a really simple principle. The valuable ore particles are almost always much, much denser. They have a higher specific gravity than the worthless gangue particles. It's just like our analogy. The steel bolts are way heavier than the plastic nuts.
So the process, which is often called a hydraulic wash, is super logical. First, you have to crush the rock into a fine powder. This is key because it frees the little ore particles from the gangue. Then, you just wash the whole mess with a strong, fast-moving current of water. The lighter gangue gets swept away, while the heavier, valuable ore particles sink and get left behind. Simple as that.
So, when does this tool work best? It's perfect for concentrating really heavy stuff, like native gold particles, or dense oxide ores like hematite, which is where we get our iron, and also tin stone. It's a straightforward, super effective method that just relies on basic physics.
But what if the ore and the gangue have pretty similar weights? Uh-oh. A simple gravity wash isn't going to work. We need a new tool, one that doesn't rely on brute force, but on some really clever chemistry. This method is called froth flotation. Now, the principle behind froth flotation has absolutely nothing to do with weight. It's all about how different particles react to oil and water. See, the valuable ore particles are hydrophobic, which is just a fancy way of saying they hate water and are attracted to oil. The gangue, on the other hand, is hydrophilic. It loves water, and we can use that difference.
Okay, so here's how this magic trick works. You take the powdered ore and mix it in a huge tank of water along with some pine oil. Then you start bubbling air through the whole mixture. The oil creates this thick froth, like a bubble bath. And because the ore particles are attracted to the oil, they stick to the bubbles and float to the top in this rich metallic foam. You just skim that foam right off the top. Meanwhile, the water-loving gangue just sinks to the bottom. It's brilliant.
This method is the absolute go-to for a whole class of materials called sulphide ores. It's essential for concentrating things like galena, which is our source for lead, and zinc blende, our source for zinc. Honestly, without froth flotation, getting these metals would be way harder and a lot more expensive. And you can make this process even more precise. Let's say you have two different types of sulphide ores mixed together. You can add another chemical called a depressing agent. What this does is it basically tells one type of ore not to float. It allows for this incredibly specific separation. It's like telling only the hex nuts to grab onto the bubbles, while the square nuts have to stay behind. All right, on to our third tool. This one leverages another fundamental property of physics. If you can't sort by weight or by surface chemistry, maybe you can use a magnet. The principle here is just incredibly simple. It only works if one component in your mix is magnetic and the others are not. That's it. This gives you a really straightforward yes or no sorting system.
The machine itself is pretty elegant. You've got the ground-up ore and you drop it onto a conveyor belt. This belt passes over a super powerful magnetic roller. The non-magnetic stuff, it just falls right off the end into a bin.
But the magnetic particles, they cling to the belt as it goes around the roller, and they only drop off once they're past the magnet, falling into a totally separate pile.
And what's really cool is how versatile this is. You can use it to pull out magnetic impurities from a non-magnetic ore, like getting wolframite out of tinstone, or you can do the complete opposite and use it to pull out a valuable magnetic ore, like chromite, from a pile of non-magnetic gangue. See, it works both ways.
So, we've used weight, oil, and magnets. What's left? Well, our final tool is the most precise and, chemically complex of them all. This is where we stop sorting things physically and start sorting them chemically, by dissolving only the exact thing we want. This method is called leaching, and the core idea is to find a very specific chemical, a solvent, that will dissolve your valuable metal but leave that worthless gangue completely untouched. It really is like having a chemical key that unlocks and liquefies only the gold, for instance, leaving all the rock behind as solid sludge.
Now, there isn't just one chemical key. The right solvent totally depends on the metal you're targeting. For example, a cyanide solution is the key for dissolving gold and silver. A strong alkali, like sodium hydroxide, is what you use to leach aluminum from its ore. Ammonia can be used for nickel and copper, while strong acids work well for zinc. The trick is always finding that specific chemical that reacts with the ore, but not with the gangue.
Here's a really famous example, the equation for cyanide leaching of gold. Now, I know it looks complicated, but the idea is actually simple. The solid gold reacts with a cyanide solution and some oxygen, and it forms a brand new compound that can dissolve in water. The gangue, it doesn't react at all. So after the reaction, you just filter out all the solid waste, and you're left with a liquid solution that contains all of your gold.
So, we've walked through 4 very different ways to separate ore from gangue, and I think it's pretty clear that there is no single best method. Choosing the right tool from the toolbox depends completely on the unique physical and chemical properties of the ore you're dealing with.
So let's just recap the big picture. If your ore is way denser than the gangue, you use gravity separation. If it's a sulphide ore that hates water, froth flotation is your friend. If one part is magnetic, you grab the magnetic separator. And if you can find a chemical key to dissolve the ore but not the gangue, you use leaching. It's all about matching the problem to the right solution. That's really the art and the science of ore concentration.
But here's something to really think about. The ores we're mining these days are getting lower and lower in quality. That means more and more gangue for every little bit of metal. Now, these old tools, they still work, but they use immense amounts of energy and water. So the final question really is, what comes next? What new, smarter, more efficient sorting tools will we have to invent to keep building our world?